Hi everyone, this is Khyati. I'm going to talk about entity skeletons for visual storytelling, and this is joint work with Roping and my professor Alan Black. This is briefly going to be the outline of today's talk. We have always been enveloped by narratives, let it be cavemen telling stories via shadows around fire, cave paintings, puppet shows, to more contemporary media, including movies, news, Instagram stories, etc. The ability to perceive and express a set of related content is fundamentally a human attribute, and with the advent of virtual beings like Alexa, Facebook Portal, Google Assistant, etc., coexisting and sharing this ecosystem with us, it is time to teach them and impart this too. With some of the recent advancements in generating text, we are moving now towards making them more natural and human-like. We address one of the properties that bridges the gap between human and machine generation, thereby making it effective in this particular piece of work. So while there are other properties such as surface form realization and structure, I'm not going to talk about those specific properties, but I'm going to focus on the property of content in this talk. For instance, the description of the first set of images talks mainly about beach, kids, palm trees, resort, etc. And the second one talks about libraries, books, etc., which are relevant for the corresponding set of images and cannot be interchanged with the other set of images. This contributes to the relevance of the text. So for content relevance, we will be looking at these entities and their references in visual stories. For instance, the first set of images, the entities include something like beach, kids, resort, umbrella, etc. And for the second set of images, it includes something like library, students, books, etc. In order to achieve this, we introduce a mechanism called anchoring. Now, what is anchoring? It is something that provides a reliable and principled support by holding it consistently and firmly. In this particular case, guidance is provided at a fine-grained level, where each sentence SK in the output narrative is guided by the corresponding anchor unit AK. Broadly, the two components in NLP are natural language generation and natural language understanding, which are NLG and NLU. And this anchoring provides for a synergy between them with a focus on generation. Here we focus on the task of generating stories from a sequence of images. In addition to generating the story, our specific task is to improve the content relevance by introducing relevant entities at relevant junctions. The two main questions that pop up here are where do we introduce entities in a story, and after we have introduced them, how do we refer to them? Formally, the dataset comprises of a set of stories. Each story constitutes a sequence of 5 images denoted by I, descriptions in isolation denoted by X, and story-like sentences in sequence denoted by Y. The input for each instance is a sequence of images and the corresponding descriptions in isolation, and the output is a story in sequence. The anchors are the entities that we are going to look at in a bit and how we represent them. We evaluate our methods on the visual storytelling data set, which has about 25% of the images that do not contain DII, which are description and isolation. And hence, we use a pre-trained image captioning model to derive DII in order to make the data set complete. The first step is to extract the entity anchors. Here, we call it as the entity skeleton. This is defined as a linear chain of entities and their corresponding referring expressions. Stanford Core NLP is used to extract these co-reference chains. We work with 3 forms of entity anchors. One, the surface form co-reference chains. The second are nominalized representations, and the third are abstract properties. First, let's look at the baseline model, which is essentially a seek-to-seek model that takes a sequence of images and generates a sequence of sentences as a story. Given a sequence of images, we first extract image features. These are the sentence level features for each image, and these local features are then passed through a couple of file STM layers to derive the overall story level context. The sentence level and the story level features are connected using the residual connection to arrive at the local context. For any given time step in the story, this is fed into each time step of the decoder to generate the sentence. In order to make a fair comparison, we augment the decoder with the entity skeleton words as well to make a stronger baseline. But directly augmenting the entity terms of the skeleton to the decoder might affect the language model. Hence, we perform multitasking, where the primary task is the generation of the story and the auxiliary task is the prediction of the entity skeleton. In any of the earlier methods, we are not explicitly attempting to capture the focus on the words within the sentence and across the sentences that contribute towards the entity skeleton. So to address this, we propose a hierarchical local context model that is built upon the baseline that we discussed before. The idea of the sentence level attention is to see which of the individual words within a sentence are contributing towards the skeleton condition generation. And similarly, the idea of the story level attention is to see which of the sentences in a story contribute towards weaving it around the given story skeleton. So first we take the embeddings for each of the words in each of the sentences from DII. We pass them through a BayLearn and attended vectors are computed with respect to the hidden states of the entity skeletons. And the latent representation from the BayLearn and the attended representation are connected through a residual network, and this operation is performed for each of the sentences. Now in this way, we derive at the attended sentence level representation, which we pass through a BayLearn to derive the global context, and we apply attention mechanism once again on these attended representations, hence the name hierarchical local attention. The corresponding latent representations are used to condition each time step in the decoder. Here are some of the consolidated results from our model that we can see. As we can see, the MTG model with nominalization and the local hierarchical attention model shows an improvement in the Meteor score. Um, we devised a distance metric just to measure the distance between generated and ground truth entities. And the last column shows the average number of distinct entities in the generated stories, and the number of the ground truth entities is about 0.7944, and it is closest to our hierarchical local attention model. We'll have a closer look at the entities in a bit. We also conducted human evaluation, which resulted in a preference of about 82% over the baseline and 64% over the multitasking model. Here is an example story. The highlighted words were generated in the right frame with respect to the ground truth story, and the baseline model got the skeleton words for sentences 4 and 5. The global hierarchical attention model could adhere to the sentence skeleton in sentences 1, 3, 4, and 5. More details of number of nouns and pronouns being generated are detailed in our paper that is available online. So the main takeaways of our work are it improves relevance component of visual storytelling. Second, it improves controllability in generation. And third, it is a step towards interpretability with respect to intermediate representations that humans can understand. So thank you so much for attending the talk at BayLearn. Please feel free to reach out to me if you're interested in the work or if you'd like to discuss more. I'd love to have a chat with you. You can find me in the conference, or you can also reach me at this email ID. Thank you so much.